prove the midpoints of the sides of a quadrilateral, alright, so the first thing I'm going to do is say, in my quadrilateral ABCD, or OABC, whatever you've made it, doesn't matter, the midpoints of the four sides are, and I'm going to make them letters as well. So here's my midpoint. I'll do my midpoints in a different color. So I'm going to make that, so A to B, I'm up to E. So that's going to be midpoint of E. Then I'm going to go F. Then I'm going to go to G. And then I'm going to go H. So it talks about the midpoints making a parallelogram. So what do I have to do? I have to show that those sides are equal and parallel. So the trick here, a bit of a trick, is to put in another diagonal. Let's put in BD. And what we're going to try and show is that HE is parallel to BD. Is that BD? Yes. And FG is also parallel to BD. Therefore, EF and FG are parallel to each other. And that they're the same length as well. So we need both of those. All right, so let's start off with, so you need to write that down too. So we've said in our quadrilateral ABCD, the midpoints of the four sides are E, F, G, and H. And you can say as shown in my picture. And we've constructed a diagonal DB. All right, so first of all, let's look at what DB is in terms of the other purples, as it were. So DB, because we're going to use DB, is, so if we go from D to B, we could have gone from D to A and then A to B. Right, we could have gone that way, and that would be the short, or the long cut, or the shortcut is the DB. All right, so we could have done that. So now let's look at HE. So remember, we're trying to show that HE is a scalar vector of DB. So it's just a scalar of DB. So let's have a look at HE. So HE, so the shortcut for HE would be, or the long way round would be HA plus AE. All right, and what do we know about HA? Let's try and express these in terms of the purple lines. So we know HA is a half of DA because H is the midpoint. And we know that AE is half of AB, vector AB, because it's also the midpoint. So now we can compare nicely because you can see they're both halves, and we've got a DA plus AB, which is from here is half of our DB. So that's, as long as you know what you're trying to head for, it makes it a lot easier. So we're trying to get HE as a scalar of our DB. So we expressed DB in terms of our DA and AB, and we expressed HE in terms of our DA and our AB, and it was half of that. So we know its length, so we can say therefore HE, whoops, it's not going to work, but that should be an H. HE is half the length of DB and parallel. Sorry, you can't read that. Now we don't have to do the FG because it's going to be exactly the same. So you can say similarly, and the pen is, here we go, starting to work again. Similarly, FG is going to be half the length of DB and parallel as well. So therefore, HE and FG are both equal and parallel. Therefore, EFGH is a parallelogram because the definition, one of the definitions of a parallelogram is one pair of opposite sides equal and parallel, because that makes the other pair equal and parallel. So yeah, as long as one pair of opposite sides are equal and parallel, we have a parallelogram.